Good afternoon, students. Today we will be continuing with the quantum mechanical model of an atom. Now, before learning about the details or the postulates of this model, let us discuss about psi. This symbol represents psi, which is nothing but a wave function. Now, psi, which is a wave function, what is a wave function? Actually, a wave function is used to denote or describe an electron. Now, what is the significance of this wave function psi? Wave function gives us an information about the energy of an electron. It gives us an information about the position and about the velocity of an electron. Okay. Now, let us view the equation which gives us the information about the electron. Now, this is the very equation which is nothing but the Schrödinger equation. So, this is the form of Schrödinger equation. It's not a very simple form. So, it's d2 psi by dx is 2 plus d2 psi by dy2 plus d2 psi by dz2 plus 8 pi square m by 8 square e minus v into psi equal to 0, where E represents the total energy and V represents the potential energy. Okay. Now, this can also be written as H cap psi is equal to E psi. Now, what is H cap? H cap is nothing but a mathematical operator. It is named as an Hamiltonian operator. Okay. Now, what is a Hamiltonian operator? It is very much an operator, mathematical operator like addition, subtraction, multiplication, division. It's an operator. Okay. Now, it proceeds with mathematical operations. Now, this is also the other way by which we can write the Schrödinger equation, and E here represents energy. That means energy of an electron. Now, we apply this operator, this Hamiltonian operator on psi. We get to know, when we apply this operator, H cap, Hamiltonian operator on the wave function psi, we get to know about the energy of an electron. Okay. Now, how to determine the position of an electron? Because we have said this psi gives us an information about the energy, the position, the velocity and all. So, if we consider psi, have a look here. If we consider psi and we take the modulus of that. So, modulus means we are not taking into consideration the sign, we are only taking into consideration the magnitude, and we square it. So, that gives us an information about the probability of finding an electron at a position. Okay. So, psi square is nothing but probability of finding an electron at a position. Okay. Now, if we concentrate here, then we will be able to find that this is the main difference between Bohr's model and quantum mechanical model. Now, the question is why? Because Bohr's model exactly states where an electron is, and quantum mechanical model tells us about the chances or probability of finding an electron. There lies the difference, right? Now, next, whenever there's a concept like there's a chance or probability of finding an electron, we cannot easily locate the electron. So, we must go beyond the concept of shells, that is concept of orbital. Okay. So, what's an orbital? An orbital is defined like this. It is the region in space where there is non-zero probability of finding an electron. Okay. Non-zero means there's a chance of finding an electron. Okay. Actually, orbital is the collection of those points where there is some probability of finding the electrons. But in reality, what happens, where the chances are very less, we don't consider them as orbitals, but where the chances are maximum, okay, that we consider as an orbital. Next, when we are speaking about orbitals, we should consider a node. So, what's a node? A node is nothing but it's a region in space where there is zero probability of finding the electron. So, node is that point, or node is that region where there is no chance, no probability of finding an electron. So, in our class we have already discussed about the wave nature of electron, where we treat an electron like a standard stationary wave or a standing wave. And what's a stationary wave, or what is a standing wave? It's that kind of a wave which is not going to travel, okay, but at least has one point where its amplitude is 0. So, that point where its amplitude is 0 is termed as a node. So, there we have discussed. Now, we are extending this one, right? Now, the next concept which we must take into consideration is quantum numbers. Now, what are quantum numbers? Now we have seen the Schrödinger equation. And if we go for solving the Schrödinger equation, we get a set of numbers. And those numbers are only termed as the quantum numbers. Okay. Now, what is the significance of these quantum numbers? In order to characterize the electron, we use some parameters. So, there are 4 parameters which characterizes the electron. Okay. So, those 4 parameters are only the quantum numbers. So, the first one is the principal quantum number, which is denoted by n. Next one is the azimuthal quantum number, which we also call as orbital angular momentum quantum number, which is denoted as L. Then comes the magnetic quantum number, which is denoted as M. And lastly, the spin quantum number, which is denoted as S. Okay. Now, if we know about these numbers, we can easily say where an electron is. Okay. Now, suppose, let us take an example. Suppose you need to locate a person. Okay, you don't know the person, you need to locate the person. Okay, only the name and designation of the person is provided to you, and some idea is given to you in which country the person is. So, how we can locate the person? First of all, we need to know the person belongs to which country. Okay, now from the very country, we must look for the state. After we find the state, we need to find the city or the locality. And after we find the city or the locality, we need to see for the very building or apartment in which the person is staying. And there are many other parameters. These are very much the gross things which I am discussing. Okay, there are very much minute things which can actually make us find the person, right? So, at least we need these 4 parameters in order to locate the person. Similarly, in order to specify where an electron is in an atom, or it belongs to which atom, we are talking about which electron, we need to take the help of these 4 quantum numbers. Okay. Now, first we will discuss about the very first quantum number, which is nothing but the principal quantum number. Principal quantum number, as we have seen, it is denoted by n. Okay. Now, this is the very first parameter to describe an electron. Now, what information the principal quantum number gives us, and what are the possible values of this principal quantum number? Now, principal quantum number can have positive integral values. So, the values cannot be 0. The values cannot be fractional or decimal like. The values will always be whole numbers like this: 1, 2, 3, 4, 5, ... like this. Okay. So, always they are positive integers, they are whole numbers. Okay. So, if n is 1, that denotes that it is the K shell. If n is 2, it is the L shell. For n equal to 3m, 4n, 5o, like this. So, actually with the help of this quantum number, we can say in which shell an electron belongs, right? Apart from this, what additional information can we get from this quantum number? That means with the help of this quantum number, if we know where an electron actually is, in which shell, we can easily find the distance of the electron from the nucleus. So, first it helps us to find the shell number. Next, it helps us to find the distance from the nucleus. Third, it also helps us to find the energy of an electron. Okay. So, these are the basic informations which we get from this very quantum number. Okay. Now, suppose you are provided with some number of electrons, and out of that you are saying that some of the electrons are having the same value of n. If they are having the same value of n, that means those electrons belong to the same shell. So, same value of n means they belong to the same shell. Okay. So, this is all about the principal quantum number. Now, next we are going to proceed with the next quantum number, which is azimuthal quantum number. Or we also call it as orbital angular momentum quantum number. Now, when we are dealing with this concept, now we should extend our concept beyond shell. Okay. Now, shell or orbit or energy level, which has been stated by Bohr, under a particular shell, always remember there are certain number of subshells. Okay. And subshells, like shells, they are always circular, having different value of radius, but subshells, they have different shapes. Let us suppose there's a subshell which is named as S subshell. What is the shape of that? That is spherically symmetrical. That is spherical in shape. Then we have another subshell, another kind, that is P subshell, which is dumbbell shaped. Then we have D subshell, which is double dumbbell shaped. Okay. Next we have F, which has a very complicated shape which cannot be represented on 2D. Okay. So I am writing complicated one. So how an S subshell looks like? S very much looks like this. It's a spherical one. Okay. So if we consider the 3-axis system, so this is its orientation. Okay, this is S. How a P subshell looks like? P subshell is dumbbell shaped. Okay, so the dumbbell looks like this. In P subshell, we are having 3 dumbbells. So the set of 3 dumbbells gives rise to the P subshell. If this is X, this is Y, this is Z. So these 3 dumbbells gives rise to the P subshell. This is the P subshell. Similarly, D subshell is nothing but double dumbbell shaped. It's very much like the 2 dumbbells are there. So this is the D subshell. Actually, there are a set of 5D double dumbbells. Okay, so those 5 sets gives rise to the D subshell. Okay, now in order to identify the subshells, we use azimuthal quantum number. So if it is the S subshell, for S subshell, azimuthal quantum number L is 0. For P subshell, the azimuthal quantum number L is equal to 1. For D subshell, azimuthal quantum number L is equal to 2. For F subshell, the azimuthal quantum number L is equal to 3. So it goes like this. Okay. Now, we see that for a particular value of n, that means for a particular value of principal quantum number, what are the possible values of L? That means what are the possible shapes of subshells which are possible. If we consider n equal to 1, that means for the K shell or the first shell, there is only one possible subshell S. For the second shell, that means n equal to 2, there are 2 possible subshells S and P. For the third shell, n equal to 3, there are 3 possible subshells S, P and D. For the fourth shell, there are 4 possible subshells S, P, D and F. Right? Now, the question arises that starting from 1 up to 4, all are having S subshell. Starting from 2 up to 4, and it goes on like this, all are having P. 3, starting from 3, they are having D. Starting from fourth shell, it's having F like this. So how to distinguish? So actually, when we write the subshell, we must denote the shell to which it belongs. So if it is S, so we will write 1S. For the second one, it is 2S. For the third one, it is 3S. For the fourth one, it is 4S. Now P starts with the second shell, P subshell. So it is 2P. Then it's 3P. Then it's 4P. Okay. For the third one, D starts with the third one. So 3D, then comes 4D. F starts with the fourth shell. So 4F, like this. Got the point? Now for S subshell, L is equal to 0. Okay. For P, L is equal to 1. For D, L is equal to 2. For F, L is equal to 3. So it goes on like this. Okay. Now always remember that for any particular value of n, for any n, What are the possible values of L? The possible values of L are from 0 to n minus 1. So L cannot have any value which is equal to the value of n. It will always have values which is 1 less than the value of n. Okay. Now what is the significance of this L? That means azimuthal quantum number. Azimuthal quantum number tells us about, or it designates about, the subshell, and it also tells us about the specific shape of the subshell or the orbital the electron occupies. Okay. Now again I am repeating, within a shell or for a given value of shell, okay, there are certain number of subshells, okay, which has characteristic shapes. Got the point? Now with the help of this quantum number, azimuthal quantum number, we can also determine the orbital angular momentum. So orbital angular momentum of an electron, which is denoted by capital L, which is nothing but equal to root over of L into L plus 1 into h by 2 pi. Got the point? So with the help of this quantum number, we can also find the orbital angular momentum. Now let us have a look at the next quantum number, which is magnetic quantum number. And magnetic quantum number is denoted by, as we have seen, small m. Now what we have seen, that under shells there are subshells, and subshells have specific orientations in space. So each orientation is known as an orbital. So M designates the specific orbital, it designates the specific orbital within a subshell. Right. So always remember that orbitals within a given subshell differ in their orientations but not in their energies. Now S subshell has no, it's spherically symmetrical along any axis. It has the same orientation because it's a sphere. But if we consider the P subshell, so P subshell has 3 sets of dumbbells, one oriented along X, the other oriented along Y, and the next one which is oriented along Z. So this one, this is which was oriented along X axis, this is termed as Px. The one which was oriented along Y axis, it is termed as Py. And this one which was oriented along Z axis, it is termed as Pz. Right. So P subshell has specific orientations. There are 3 possible orientations. So we can say Px, Py and Pz, they are the orbitals. Got the point? Is it clear? Similarly, if we consider the D subshell, it's double dumbbell shaped, but there are 5 possible orientations. Okay. So we can draw the double dumbbell like this. If this is the x-axis, this is y-axis. So this is designated as dx square minus y square. Similarly, there's another one which is dz square. One dumbbell is like this and another dumbbell is oriented perpendicular to it and it's constantly in motion. So it's appearing like a ring. Okay, it's actually not a ring, it's a double dumbbell only, but it's very much in high speed rotation. So this is dz square. And there are 3 other orientations. This one, it is dxy. Next one, dyz. And we have dxz or dzx, whatever. Okay, so these are the 5 possible orientations. Now these 2 are oriented, these are two such cases where the lobes are oriented along the axis, and in case of these three, the lobes are oriented in between axis. Right? So these are the 5 possible orientations. Okay, but all of them have the same energy. If the orbitals, they have the same energy, they are termed as degenerate. Okay, they are termed as degenerate. Now, always remember that when we have started with the principal quantum number, how we have related the azimuthal quantum number with the principal one. For a given value of n, the possible values of L are 0 to n minus 1. Now, for a given value of L, what are the possible values of m? The possible values of m are minus L, 2, 0, 2 plus L. Okay, got the point? So, if we consider the S subshell, for S subshell L is equal to 0, so what is the value of m? M is also equal to 0. For P subshell, the value of L is 1, so what are the possible values of m? Minus 1, 0, plus 1. So there are 3 possible values. For D subshell, L is equal to 2. So what are the possible values of m? It is minus 2, minus 1, 0, plus 1, plus 2. For F subshell, the value of L is 3. So what are the possible values of m? It is minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So for S subshell, there is only one possible value of m, so there is only one orientation. Okay. For P subshell, there are 3 possible values of m, so there are 3 orientations. For D subshell, there are 5 values of m, so there are 5 orientations. For F subshell, there are 7 values of m, so there are 7 orientations. So S subshell has only one orbital. P subshell has 3 orbitals because 3 different orientations. D subshell has 5 orbitals since it has 5 different orientations. Similarly, F has 7 orbitals. F subshell has 7 orbitals. Right? So this is all about our magnetic quantum number. And last, we are going to proceed with the spin quantum number. Now, what is the significance of spin quantum number, which is denoted by small s? Okay, spin quantum number refers to the spin of an electron. It refers to the spin of an electron. Okay, that means it also says about the orientation of the magnetic field produced by that spin. Okay, and next thing, orientation of magnetic field produced by that spin. Okay, now for every set of n, L and m values, S can have values. Which are the possible values of S? It can either be plus half or it can be minus half. Okay, so S can be plus minus half, nothing else. Okay, and from S, okay, we can determine another thing. What's that? From this very value of S, we can also find the spin angular momentum. So spin angular momentum, it is designated by capital S. It is nothing but root over of S into S plus 1 h by 2 pi. So S means the value of the spin. Okay, spin quantum number. Okay.